All right, so as promised, we are now going to talk about all of the different properties of water. In this section, you should be able to describe the properties of water, explain the role of hydrogen bonds in the properties of water, and summarize the structure of the pH scale and the importance of buffers in biological systems. So water is going to be the most abundant molecule in organisms. It makes up about 70% of the total body weight. Now, as we kind of mentioned earlier, water is a polar molecule, which means that the electrons spend more time around the oxygen than the hydrogens, and this creates a very partial negative charge. So from the electron model of water, we can see the shape of a water molecule. And a key mantra to remember in biology is that structure equals function. This is true at nearly every organizational level. The particular shape and polarity of water molecule leads to the formation of hydrogen bonds. What you'll see here is that these hydrogen bonds are caused by the attraction of the partial positive charge of the hydrogens to the partial negative charge of the oxygen of the surrounding water molecules. So these hydrogen bonds are going to be designated by these dotted lines that you see here. These hydrogen bonds are simply the attraction between this partial positive and this partial negative, and this partial negative to this partial positive, and this partial positive to this partial negative, and this partial negative to this partial positive. In this way, all of these water molecules are actually electrically attracted to each other. Now, individually, hydrogen bonds are relatively weak. They're much weaker than ionic bonds. Ionic bonds are going to hold atoms into a molecule. Hydrogen bonds are simply attractions between molecules. So they're kind of like a bunch of weak magnetic attractions. So individually, those hydrogen bonds are relatively weak. They're very easy to break. However, collectively, they're pretty strong. And hydrogen bonds are not just specific to water. They're not just found where hydrogens are present. They are found anywhere where there is a partial positive and a partial negative charge. This is going to be absolutely vital to the structure of DNA and protein molecules. So we're going to see these hydrogen bonds come up again and again and again. So make sure you are comfortable with these hydrogen bonds. So like I said, a hydrogen bond is an attraction between a slightly positive hydrogen and a slightly negative oxygen or nitrogen. This is going to be depicted by dotted lines. And like I said, they are relatively weak bonds, significantly weaker than ionic or covalent bonds. So, because of those hydrogen bonds, water molecules are going to cling together. It's this association that gives water many of its unique properties. For example, water's high heat capacity. Heat capacity refers to a substance's ability to absorb energy without actually changing in temperature. Water requires 1 calorie to raise the temperature by 1 degree Celsius for 1 gram of water. Just as a reference, other covalently bonded liquids require about half as much energy. There is a lot of energy required in order to increase the temperature of water. And it's because of the presence of those hydrogen bonds. It allows water to absorb energy without any great change in temperature. Water also holds on to its heat. Its temperature falls much more slowly than other liquids. This slow change in temperature is absolutely essential for all life on Earth because the temperature rises and falls so slowly, organisms that are comprised of mostly water are able to maintain their internal temperatures even in the presence of rapid external temperature fluctuations. This is why you can go outside where it's 100 degrees and then go inside to an air-conditioned building where it's 62 degrees. And although you feel the temperature change because you have temperature receptors in your skin, you feel the change, your internal body temperature does not change. You're going to maintain your 98.6 internal body temperature regardless of those sudden fluctuations outside. So hydrogen bonds have to be broken before water can boil. This is also going to require a huge input of energy, and converting 1 gram of the hottest water into a gas is going to require a huge input of energy, roughly 540 calories of energy. This equals water's high heat of vaporization. This high heat of vaporization is the amount of energy that it takes hot water to boil. So first, The high heat capacity, it requires a lot of energy just to heat water up, but to actually break those bonds enough to turn that liquid into a gas requires an even more insane amount of energy. Water's high heat of vaporization gives animals in a hot environment an efficient way to cool down, to release excess body heat through sweating. When the human body begins to sweat or gets wet, the body heat is used to evaporate the water off the body, thus cooling the organism. Water's high heat of vaporization also means that coastal climates tend to be temperate. During the summer, large bodies of water, such as oceans, tend to absorb and store solar heat. During the winter months, this heat is then released very slowly. So here in the Midwest, we tend to be far away from large bodies of water, and so we experience really drastic and sudden climate changes. You'll see this a lot in the winter where it'll be, 12 degrees one day and then it'll suddenly be 40 degrees the next day. We see rapid changes in temperature because we're not really near any large bodies of water. I grew up in Green Bay, Wisconsin. So that particular portion of Wisconsin is surrounded by lots and lots of large bodies of lakes and waters. We're up by the Great Lakes. And what we found is even though we lived, many, many miles inland, because we're still so near water, the temperature doesn't change very drastically. In the summer, temperature stays roughly between 75, 85 degrees all summer long. Late August, we'll start to get some really high, hot days where it gets, all the way up to a boiling 92 degrees. But for the most part, it stays relatively temperate all summer long. Now, which is beautiful. That's wonderful. I enjoyed that part of living in Wisconsin very much. However, what we found as well is that in the winter, being so near those large bodies of water, it also causes the weather to not change very drastically. Once it gets below 30 degrees, it stays below 30 degrees all winter long. And winter can, be 5 or 6 months. So it would get below 30 degrees in November, and it would stay that way until April. We would get random surprise days where, it had been negative 14 degrees for a week in a row, and then all of a sudden it would be like 2 degrees. We'd actually have it above freezing, but that would be as severe as our temperature swings would get. We really didn't get any surprise temperatures above freezing for months at a time. And it's due to water's high heat capacity and high heat of vaporization. It requires a lot of, energy in order to actually change the environment. All right, so due to its polarity, water is also a particularly good solvent, especially for polar molecules. A solution contains dissolved substances known as solutes. Molecules that can attract water are said to be hydrophilic. Hydro meaning water, phileo meaning love. So it literally means water-loving in Greek. Non-ionized and polar molecules cannot attract water. Those are going to be said to be hydrophobic. Hydro, again, meaning water, and phobos, meaning to fear. So hydrophilic molecules tend to attract other polar molecules. Hydrophobic substances tend to associate with other non-polar molecules. So for example, gasoline is a non-polar molecule. It does not mix with water. It's considered hydrophobic. Please make sure you review hydrophobic, hydrophilic terminology. You're going to see this again over and over throughout the rest of the semester. So like I said, hydrophobic means that the molecules do not attract water. They're going to be nonpolar. In a nonpolar covalent bond, the electrons are shared equally. There's no partial charge. Because there are no partial charges, we're not attracted to water. Water is full of partial charges. And so if we have a non-charged molecule, it's not going to mix or interact with water very well. So another property of water is that water is both cohesive and adhesive. Cohesion refers to the ability of water molecules to cling to each other. This property is due to that hydrogen bonding. And it's because of its cohesive properties that water can exist as a liquid under the normal temperatures and pressures present at the Earth's surface. Adhesion refers to the ability of water molecules to cling to other polar surfaces. This property is due to water's polarity. Multicellular animals often contain internal vessels in which water assists in the transports of nutrients and wastes. And the cohesive and adhesive properties of water allow blood to fill the tubular vessels of the cardiovascular system. It also allows the transport of water in plants. So there you go. Another property of water is that a very unique property of water is that as liquid water cools, it becomes less dense. As liquid water molecules cool, they move closer and closer together, but they're still moving. However, at temperatures below 4 degrees Celsius, only vibrational movement of the molecules occurs, meaning that the molecules are no longer moving freely and flowing past each other. They remain still and continue to vibrate in place. However, at these temperatures, the hydrogen bonds become more rigid and more open. This causes water to actually expand as it freezes, and then as it freezes and reaches 0 degrees Celsius. So the density, as we go down in temperature, we've got these very, very low temperatures. Water is very, very dense. But as we near liquid, we get sort of this open, frozen crystalline structure. So this property is why cans of soda burst in the freezer, or we get frost heaves on the road in the winter. This expanded nature of water when it's solid means that ice is less dense than liquid water, so thus ice floats in water. Why is this so important? Why do we list it as one of the really awesome properties of water? Okay, I'll just tell you. If water behaved as other substances, it would be most dense as its solid state, and ice would sink. Instead, water freezes from the top down. It can actually act as an insulator to prevent the water below it freezing. This is why ice floats. And so the surface of a lake that freezes can actually insulate the rest of the lake, prevent the rest of the lake from getting so cold that the animals and organisms inside that lake freeze. So this is a really, really awesome and very unique property of water. So those are our properties of water. Next, we're going to discuss acids and bases. Acids are going to be substances that dissociate in water and release hydrogen ions. Hydrogen ions are simply, you're also going to hear this referred to as a proton. A hydrogen atom is simply a proton and an electron. If we get rid of that electron, we're left with only a proton. We also call this a hydrogen ion because it's a hydrogen atom that is positively charged because it's missing its electron. So hydrogen ion. For example, hydrochloric acid is produced by the stomach. It aids in digestion. And when you mix hydrochloric acid and water, it's going to break up into hydrogen ions and chlorine ions. This is how we define an acid, as a molecule that breaks apart to release hydrogen ions. So acidic solutions like lemon juice, tomatoes, and coffee all disassociate in water and release those hydrogen ions. The acidity of a substance depends on how fully it dissociates in water. Strong acids dissociate fully in water. Weak acids only dissociate partially. Bases are going to be substances that take up hydrogen ions or release hydroxide ions. If a strong base is placed in water, the number of hydroxide ions is ultimately going to increase. So an example of a strong base would be sodium hydroxide. Sodium hydroxide is going to break apart in water to release sodium and hydroxide ions. The pH scale is used to indicate the acidity or the alkalinity of a solution. Alkalinity is the official scientific term for basicity, how basic a solution is. The pH scale measures that concentration of hydrogen ions in a solution, and it ranges from 0 to 14, with 7 representing true neutrality, where the concentration of hydroxide is equal to the concentration of hydrogen ions. Since water disassociates evenly into hydrogen hydroxide ions, it's considered neutral at a pH of 7. Anything below pH of 7 is considered to be acidic. Anything above a pH of 8 is considered to be basic. The pH scale is a logarithmic scale. That just means that each unit of change represents a 10-fold change in hydrogen ion concentration. So as you move down the pH scale from 14 to 0, each unit is 10 times more acidic than the previous unit. So, for example, if pH of 7 is 10 times more acidic than a pH of 8, pH of 6 is 10 times more acidic than a pH of 7. So how much more acidic is pH 6 than pH 8? 100 times more acidic. So it's very important that organisms are able to maintain a standard pH to help maintain their homeostasis. And this is going to be done through the aid of buffers. Buffers are going to be, a buffer is a chemical or a combination of chemicals